Talk about sequences and series. So we want to talk about the formulas. So your formulas for arithmetic, your formula, and I think IB uses the terminology a lot, like what's the general expression for the nth term, or like find the nth term. So for an arithmetic sequence, we usually write it as the first term plus the common difference times n minus 1. It should totally make sense. If you plug 1 into that, it's just the first term. If you plug 2 in, it's the first term plus the common difference only once. If you plug 5 in, it's the first term plus the common difference 4 times, because that's how you find the fifth term. You take the first and add the common difference 4 times. It's a very common sense type formula. Then the formula for the sum of the first n terms of an arithmetic sequence is the number of terms you're adding together divided by 2 times the first term plus whatever the last term or the nth term is. Lots of times you don't know that. You have to use like this formula. Like maybe they say add together the first 100 terms. So you're going to use this first formula to find out what the 100th term actually is. So sometimes they use the combination. Shall we prove that formula for the series? Or not? You shouldn't. I want to know if I can just whip it up.
Do you think you can prove it without looking at anything?
Sure. It's not that bad. Right? Isn't that what a
something, and then you can track it out, you can track something, then you get the first and then.
Well, yeah, we can. Oh, this is different than the proof the book does, but yeah, we can factor a1 out. With what? Yeah, I don't think that's the right way to go about it. Yeah. 2e. I feel like it was something like simple but creative. The arithmetic series. Well, do you know the history behind the arithmetic series with mathematician Carl Friedrich Gauss? So the whole idea is, the story is, Gauss was one of those really annoying young kids, like, teacher, always bothering the teacher. And so the teacher, in order to, great. So the teacher, in order to keep the student busy and shut up for a while, said, just go add up all the numbers from 1 to 100. And Gauss is 5,050, like boom, like that. And the teacher was like, what? Just like that. And so they asked him how he did it, and what he did was he paired 1 with 100, and 2 with 99, and 3 with 98, and so on and so on and so on. Every one of those adds up to 101, and you know there's going to be 50 of them. And so multiply those together, you get 5,050, which is the first term plus the last term, it's a1 plus an, times how many terms you're adding together divided by 2, which in this case is 50. Isn't that pretty cool? So here's what I want to do. Here's our proof. We're going to use that as inspiration. So we got a1 plus a2 plus a3 plus, he was supposedly like single digits ages, like 7 or something. We'll say a sub n minus 2, a sub n minus 1, a sub n. Does that sound good? And I'm going to add that to itself. I'm going to add an s sub n to this, except for I'm going to add it backwards. Right? So you're going to have 2 S sub n's equals a sub 1 plus a sub n, a sub 2 plus a sub n minus 1, a sub 3 plus a sub n minus 2, and so on and so on and so on, right? And using this formula, can't you easily prove that this plus this and so on and so on and so on are actually all the same thing? Right? Isn't a sub 1 actually isn't a sub 2 actually a sub 1 plus d? And isn't this going to be, what's this going to be? A sub 1 plus n minus 2d? So if you distribute and combine like terms, this simplifies down to a1 plus an. Every one of these, right? So you can easily show, but I don't want to spend that too much time, that this is also a1 plus an, and this is the same thing as a1 plus an. How many total a1 plus an's are there? There are n of them. So what we now have is 2 s sub n equals n times a1 plus an. So if we divide by the 2, there's our formula. Does that make sense? So it's the same, the formula is just easily proven using the same exact techniques that Carl Friedrich Gauss, it's German, you have to say it like that. Carl Friedrich Gauss was noted for. He's he's my favorite mathematician, Gauss. You should read about him. If you're ever bored, I don't have my books out. I've got a fascinating book. If I can find it very quick. Sorry. Oh, I gotta hang my calendar too. Like, oh, Legos.
Wow, that's so cool. Did you buy it for yourself?
I did. I have not.
I would
Is it awesome?
You should go.
I love it.
Can I open it? Can we open it?
No, not now. We're doing that.
Why can't we just do it?
Oh, no.
How does everyone breaking their book?
Okay.
Not opening it.
I've got a fascinating book called Mathematical Scandals. Yeah, it is the drama. But there's a story in here about Carl Friedrich Gauss and how he was like, it was crazy. He was a little neurotic about his proofs, and he would not publish anything unless it was just absolutely perfect. And so they actually found after he died, like years after he died, 100 years after he died, they stumbled upon these notebooks where he had proven things that he never published and nobody knew he had proven, and actually mathematicians decades after him proved it, but he had already done it. And so even though he was brilliant, some people actually blame him for holding mathematics back like 100 years, so we could be farther along. That combined with, while he was alive, everybody was trying to prove Fermat's last theorem, and while he was in his prime, some organization offered a money reward to anybody that could prove it, so all mathematicians stopped what they were doing and spent the rest of their lives trying to prove this theorem. Except for him, he didn't want to do it. And people begged him, like, you know, nobody's going to be able to do this. Everybody's going to spend their life trying and fail and therefore not advancing mathematics. But if anybody can do it, you can. So please do this so everybody else can get back to their normal math. And he said, no way, I'm not going to do it. And by the way, Fermat's last theorem did not get proven until the 1980s.
When was the first?
1700s? Older than that? I mean, yeah. So that's the scandal, is Gauss holding mathematics back 100 years. It's fascinating. But he was brilliant.
Wait, so
brilliant.
I don't understand what you mean when you say that unless it's perfect. If it's perfect,
Yeah, but but you find flaws in proofs a lot. Like, because a lot of times you use an assumption or you use somebody else's proof, you use somebody else's work. Like, because of this, I can make this statement. Well, what if that ends up being wrong? Or sometimes these proofs get so complicated, it's hard to keep track of everything and all the logic and all the logic rules. there's often flaws in them. When I was in college, there's one of the biggest proofs of my lifetime. People proved that you can create an algorithm that tests if a number is prime or not, that runs in what's called polynomial time. That had never been done before. And so that's great. If an algorithm can run in polynomial time, it's actually reasonable. What that means is the amount of time the algorithm takes to execute is a polynomial of the size of its input. So you put in a giant, giant number, some polynomial of that number will determine how fast the algorithm runs. Up until then, algorithms to test if a number was prime or not ran in power time. And so therefore, if your number you're testing is huge, it would take centuries before the algorithm finished. So that was huge, and I actually found a flaw in their paper. It did not make the paper false. It was just a minor flaw that you could easily have fixed. But I remember, because I was working with a professor, right? I was working with a professor going through this proof, and there's part of it that didn't make sense to me. And through having a dialogue with him, he realized, like, oh yeah, you're right. They should have said this. It doesn't change anything, but it was just a minor flaw. Well, sometimes those minor flaws change everything. And so he was scared of that. Scared it would make it false. So there's the formulas for arithmetic, sequences, and series. For geometric, you've got the nth term is the first term times the common ratio to the n minus 1, right? Now, you might remember from calculus last year that sometimes the formula didn't look exactly like this, because if you're doing sigma notation, sometimes the summation index starts at a value of what? 0. And so maybe it's the first term times RGN, you know? So depending on how your index is written and what your initial numbers and subscripts are, you know, make sure you can be flexible with that. But the concept is still the same. You have the first term. The second term is the first term times the common ratio just once. The fifth term is the first term times the common ratio 4 times. Okay? So that's a geometric sequence. What's the formula for geometric series? Isn't it like the first term times 1 minus r the n over 1 minus r?
Yeah.
Something like that?
So, wait, is the big S, is that a sum or a series?
It's a capital S that stands for sum, the sum of all the numbers in the sequence. Yeah, see, that's the thing. Most of those problems are from tests where they did not have the no calculator rule. And so I believe in the past, those tests were created knowing that people would have calculators available but may or may not use them. So you can kind of get a feel from some of the problems where you have to use a calculator. Like it's obvious the answers to these weird decimals. But I would say for most of them, try and do them without a calculator. I mean, it's definitely an analysis you're going to want to do. Now, any of the problems towards the end of the packet are from the 2008 exam, and that was the first exam that had those separated. And I can tell you which problems are none, which problems are with. I should have done that. I can do that. And then, what else was I going to say? Oh, another thing. This is different from AP. In IB, if you use your calculator and you get a decimal answer, it's 3 sig figs. Not 3 places after the decimal. It's 3 significant figures. Yeah. So, you know, if you get like if it's a population problem and you got some giant population in the billions, it comes weird, unless it specifies otherwise. Now, the nice thing is, if you make a rounding error or you round to the wrong number of sig figs, they take a point off, but it's a point towards your whole paper, and you cannot lose that point again. So if you have 3 rounding errors throughout your whole paper, you only lose 1 total point for the paper. It's not bad. Yeah. Sacrifice that point right away. Unless the rules change, but I'll look it up again. But that's how it is. But they might specify otherwise.
The answer's like 3. Would you substitute 3.0?
I would. It depends. What type of 3 is it? Is it a calculated 3 or is it like? Right. I mean, I think it depends on the context of the problem. If they're saying If they're asking you to solve x squared plus 6x plus 8 equals 0, which they won't, but if that's the problem, solve this, then you say x equals -2, x equals -4. You don't have to put the point 0, 0. But right. So like, what if this was 8.0? Instead of just 8, yeah, then maybe. I don't think they're going to be too picky about that on a problem like that. It's pretty obvious when you're using your calculator, you're getting this giant number that you have to round. It's pretty much only when you have to round. Does that make sense? Yeah. It's never going to come into play in paper 1 where you don't have a calculator. You know? There's no rounding going to happen there. And then, if the common ratio is between -1 and 1, then you have the sum is just 1 over 1 minus r. That first term. My bad. First term divided by 1 minus r. Because the idea is this. If your common ratio is a fraction, it's a number between -1 and 1, then what's going to happen to r to the n as n approaches infinity? It goes to 0. So you just have the first term, 1 over 1 minus r. So that's the idea. And it is convergent because it's a geometric progression. Is that what your calculus textbook said? Convergent because of GP. I was like, what is GP? Geometric progression. Do you want to prove that one?
Does it really matter?
Yeah, it's fun.
No, I'm saying does it matter if we want to or not?
No, I'm doing it anyway.
Exactly.
Okay.
So that's only if n approaches infinity.
If you're actually, not if n approaches infinity, if you're actually asked to actually add together all infinity of the numbers. That's one of the weird things about an infinite sum is like, what is the sum of all infinity of the numbers? Just, it's kind of weird. Because I had this discussion with a student years ago. In my, what is 0.9 repeating? It is equal to the number 1. It is the same thing as the number 1. You can use the concept of a geometric series to prove that, because 0.9 repeating is just 0.9 plus 0.09 plus 0.009 plus 0.0009, and so on. That's a geometric sequence where the first term is 0.9, the common ratio is 1/10, right? So your infinite sum, so I should put an infinity symbol there, my bad. Your infinite sum is the first term, 0.9, over 1 minus 1/10. So that ends up being 0.9 divided by 0.9, which is, in fact, 1. Well, this particular student showed me all of this work and thought he was proving to me that that is proof that it's not equal to 1, that it approaches 1. Because he's saying it's an infinite series. You're not actually adding together all infinities of the things. You're approaching what the sum of infinity would be. So you're approaching 1, but you'll never actually hit it. And I was like, kind of not exactly how it works. It's actually adding together all infinity of them. What would the infinite sum be? And it would be the number 1. I love the visual. This is an SL problem. I'll try and do it as best I can. If you've had me in Algebra 2 or pre-calc, you've seen it. But let's take a square where I shade in this square. And let's break the bottom right one and shade in this one. Let's break this one. Yeah. Oh, yeah, because... And so if I do this literally forever, an infinite number of times, and if this is a 1 by 1 square, what is the area of the shaded region? It is exactly 1/3. Okay? Conceptually, it makes sense. Ignore this square for now. What fraction of this portion is shaded? 1/3. What fraction of this region is shaded? 1/3, 1/3, 1/3. So conceptually, it makes sense that 1/3 is shaded. But you can also create a geometric series and actually add together all infinity of the numbers in the geometric series, and you will get 1/3. Pretty cool. because I think this is actually 1/4, right? And this is a fourth of a fourth, so that's 1/16, and that's a fourth of a fourth of a fourth. So what's 64, and so on and so on and so on. So your first term is 1/4. Your common ratio is 1/4. So you have 1/4 over 1 minus 1/4. 1/4 divided by 3/4. That is 1/4 times 4/3, and there's your 1/3. Pretty cool, right? That's an SL geometric series problem. But it's like it walks them through it even more. It's even easier with the way they break the problem into pieces. But yeah, the geometric series formula, how does that work? Well, S sub n is the first term plus the first term times r plus the first term times r squared plus the first term times r cubed. Agreed? This is what a geometric series looks like. Now, I'm going to factor an a1 out. That gives me 1 plus r squared plus r cubed plus r to the fourth. Now, I'm going to use something that I believe can be common knowledge, but you may not have ever learned it yet. But if I have x to the n minus 1, what can any polynomial of this form factor down to? It's always factorable. What is always a factor of x to the n minus 1? X minus 1 is always a factor of that. What's the remaining factor, however? It's going to be, well, the first term, if the first term here is x, this one has to be x to the n minus 1. Yeah, it's not really, it is like, okay? So that is something that I should be known, but not a lot of people know it. So for example, x to the 7th minus 1 becomes x minus 1, x to the 6th plus x to the 5th plus x to the 4th plus x to the 3rd plus x squared plus x plus 1. So what this means is, if we divide this to the other side, x to the 6th plus x to the 5th plus x to the 4th plus x to the 3rd plus x squared plus x plus 1 is actually x to the 7th minus 1 over x minus 1. Agreed? Well, isn't that essentially what we have here, but instead of x's we have r's and it's actually written backwards? So can't I replace 1 plus r to the 2nd plus r to the 3rd plus r to the 4th, and what's my last term? Isn't it r to the n? Or, is it r to the n? Or is it r to the n minus 1? I think we want to say n minus 1. Right? Because won't the nth term be r to the n minus 1? So then this becomes a1 times, according to this pattern, r to the n minus 1 over r minus 1. And that's the formula right there. Except, that's not actually our formula, is it? Don't we write it as 1 minus r to the n over 1 minus r? Right, and why are they the same? What's the difference between r to the n minus 1 and 1 minus r to the n? They're opposites of each other. But aren't I taking the opposite here? They end up with a negative over a negative. That's all good. Cool? I like these. That is also not how the book proves that one either. The book's got different proofs. The book does it in a way that does not use this pattern. That's good so far. 2 proofs. Totally winged. Wing. That's good. I do better with the harder proofs. Okay, so any specific questions? So we've talked about the basics of arithmetic and geometric sequences series. Now what about the specific? Number 4. Excuse me. Here, let's whip up this problem packet right quick. Yeah, I'll have it.
Not at all. Is it like in a rut? Where?
Okay, number 4. My favorite. Did anybody get to the one that's like it's an area of a sector problem, but it's a geometric sequence? So you take a circle and you have a sector, and then the next sector is bigger, and 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 the areas of the sectors in order form a geometric sequence, and then it's like find the ratio of the last sector to the first sector or something. It's a cool problem. Look at that. I think it's in your problem packet. Should be. It might be towards the end. I'm not sure. Okay, number 4. It's a good one. The ratio of the 5th term to the 12th term of a sequence in arithmetic progression is 6/13. Actually, let me snip this so that I can write. Okay. So the ratio of the 5th term, a sub 5, to the 12th term, a sub 12, is 6/13. Another way we could write that is a sub 1 plus 4d over a sub 1 plus 11d, right? If each term of the sequence is positive, and the product of the first term and third term is 32, find the sum of the first 100 terms. Wow, that's a good one. This is a good one to start the year off with. It's one of the more challenging ones, I feel. And that's early in the packet. That's from like 1999. I was still in high school then. Okay. So let's call this a sub 1 times a sub 1 plus 2d. Well, what do we got here? We got 2 equations with the same 2 unknowns. That's just a nice nonlinear system of equations. Right? Your unknowns are A1 and D. Oh. Yeah, no, that part is... Now, here's the thing. They want us to find the sum of the first 100 terms. The sum of the first 100 terms is going to be 50 A1 plus A100, also known as A1 plus 99D. So is there any way I can extract from either of these what this stuff is? No, I'm pretty sure. It's looking like you're actually going to have to find out what A1 is and what D is, and then use them to find the sum. Gross. I think your best bet is solving for this D. Honestly. Get out of here with your gifts and shit.
That's like,
Hey, to be on the test, if it works, go for it. Yeah.
That is what I took A1 plus 11D multiplied it on to the left, and then took the 13 multiplied it on to the right. Found the ratio of A1 to D, then I took 2D, A1 is the 2D on the right equation.
So you had 6A1 plus 11D equals 13A1 plus 4D, right? And then did what?
Well, multiplied through 6A1.
Okay. Okay. And then combine it all up. So you get something like this 14D equals 7A1. So then you did the ratio of A1 to D. So you had 2 equals A1 over D. I like it. And then what you do? Or even better, you call A1 2D. And then just substitute it in up here. So you have 2D plus 2D. Oh, that's nice. That actually worked out great. So you get 8D equals 32, and so D is 4.
Wait,
huh? Well, 2D plus 2D is 4D. Ah, D squared. Ah!
come on.
Ah! So early in the year still. So you do have a potential on your common differences. Is it positive 2 or negative 2? But I told you all the terms have to be positive. You can't possibly have a common ratio that's negative with all your terms still being positive. So you throw that one out. I like that.
Go back to the first step. Was it just cross
multiplying? Yeah. This is multiplied by the 6, the 13 is multiplied by that.
Okay.
Yeah. Distribute, combine like terms, so you get this. So it's essentially, we're solving a system of equations by what method? Substitution. We are solving this equation for A1. Right? And look how nice it turned out. A1 is 2D. That was great. So then you plug 2D in here, and you get D equals positive 2. You throw out the negative 2.
How did you get from like A1 times A3 equals 32 to A1 times A1 plus 2?
Isn't the third term of the arithmetic sequence just the first term plus 2 of the common differences?
Oh, so you just changed that.
Using that nth term formula.
Okay.
Yep.
I thought you were taking out.
That was great. Then we can plug 2 in here, and what's the first term? 4. So then we can find the sum of the first 100 terms. 50 times 4 plus 4 plus whatever 99 times 2 is. Figure that out. You're good to go. Oh, sweet. What do you mean? No, I don't think so. No, like see what I did? I just immediately threw that together. I think that's a great first step. Yeah, no. No, I think as far as showing work goes, that was great. This is funny. Maybe a little bit more organized, like I just jumped over there. But no, that's good. Very nice. That was cool. Does it say how many points that was worth? 7?
Not big at 7 minutes.
That's pretty normal. Sometimes they did not used to adhere to the 1 minute per point rule. So some of these problems in here, like every once in a while you'll see a problem that's packed at 3 points. You'll never see a 3-point problem anymore. Because that 3-point problem actually should take you 10 minutes. They didn't used to do that 120 points under 20 minutes. So sometimes you can't quite follow that, but that to me, 7 marks, 7 minutes for that, that's probably the way they would do it on a modern test. So short response problems never get more than 9 points, never get less than 5. Go back to the work. I like that one. That one's good.
What was the final answer?
10,300? That's what I got. Is that right?
Oh, yeah. I just didn't look off that other thing.
So how does that tablet help you develop? Oh, really? Is the game you're making for Xbox? Oh, just for Windows 8? Very cool. How many people are in his company? 10? Wow. Very cool. More questions?
Can you do 33 part C of question? Well, it's just a subject.
I mean, if you're skipping around to the arithmetic sequences and series, like 33. Consider the arithmetic series. 2 plus 5 plus 8. Oh, that's nice. I got the first term. I get the common difference. Find an expression for S sub n for the first n terms, okay? Well, let's kind of jot down what we know. The first term is 2. The common difference is 3. So what is the nth term? It's going to be 2 plus 3 times n minus 1, yeah? So therefore, the series is going to be n halves, first term plus nth term, so that turns out to be n halves 2 plus 2 plus 3n minus 1. And then if you want to simplify that down, you can end up being quadratic. I don't think they take off for not simplified. No.
Or should you add into?
You want to? They basically have a rule that states any variation of the right answer is correct. And any work you do, let's say you do a problem and you get to what they determine is the ending right answer, but for some reason you continued on and did more, they aren't supposed to grade any work that comes after your final answer.
That's nice.
So if that's the case, then in theory, once they get to anything that counts as the correct answer, they shouldn't be grading it anyway. Right. But I can't imagine that. These graders are human. They grade very different. Everybody, you know. So you never know. I would simplify it. I could see some of the graders, yes, marking that wrong. Yeah. Because they're still human. They still have their own judgment, even if it's against the grading guidelines. But, yeah, they could just be like, this is obnoxious. Now, the thing is, you might need to use this formula in the next step of the problem, so that might make the problem easier if you do simplify this down. I don't know. So I would go ahead and personally.
And you just set that equal to a bad and give you 60.
So you have n halves 3n plus 1. So I'd probably call this 3 halves n squared plus n halves. Or this even. This is nice. This is nicer. So then they want you to find what is the value of n that gives you a sum of 1,365. Well, that's really easy. What do we do? Yeah, you just set this. Now, this is the reason you're going to want to have it simplified. I want to set this version, 3 halves n squared plus n halves equal to 1,365. So something I might do is I hate fractions, so I'm going to multiply everything by a 2. So what do you get when you double that? 2,730? Is that correct? So then it should be factorable, right? Because what type of number should n be? Should be a whole number. If this is a paper 2, this is more like a paper 1 no calculator problem. But on one of the tests you don't get a calculator at all. Yeah. Yes, we can. So you can use polysolver versus quadratic formula, or that's factorable. It has to be factorable because then it has to be a whole number. So a lot of guess and check. Yeah, we can spend a day getting all the F. Well, we can find time for it.
Can we go through complex numbers tomorrow?
So start measuring next, you're going to go through induction.
I don't like proof by induction. We do that like lactose the most freshman line.
It comes up, you're going to need to, it comes up in every single topic we did. Proof by induction. They're matrix proof by induction. I'm ready for that. Do we go good up things and serious measure? Yeah, we're good for us. Oh, it's mine. Slow, hurry up. I have a few bucks. Good, I want to put my books away. Leon! Go, Paul, come on! Yeah, probably my mom is calling.
Nice dribble.
Wait, who left their bucks?
Kelly's. Oh, those are
Grant.
grants. I'll give them to him.
Not another one you challenge.
Comments about mine.
It could be from an option test.
Oh, it's this one right here. Consider the infinite geometric cube.
Geometric.
For what value for that?
Because what you're going to do is figure out what's the common ratio. It looks like the common ratio is 2/3 x.
And if it's less than 1, then it's red, right?
So you
So like I know how to do that, but
absolute value of 2/3 is
I think that's the only other thing on here.
less than 1. And just solve that on that. You have
And if,
x can be less than 6.
oh,
So yeah, you'll have 2x over 3 is less than 1, and 2x over 3 is greater than -1. You're going to have x has to be less than 3/2, but also x has to be greater than -3/2. Any x can be any number between -3/2 and